Look up at the night sky. The stars you see, the galaxies, the immense vastness of space, all of it began somewhere, somehow. But what if we go back? Back before the stars, before the galaxies, before the universe itself. What do we find? Nothing? But what is nothing? And if there was nothing, how did something, our universe, come from it? Welcome to today's journey into the cosmos, where we explore one of the most profound and puzzling questions humanity has ever asked. What came before nothing? To understand what came before nothing, we must first grasp what nothing actually is. It's a word we use often, but its true meaning is elusive. Philosophers and scientists alike have grappled with this concept for centuries. Ancient philosophers like Aristotle believed that nothing could not exist. There was always something, even if it was just potential. To them, the idea of absolute nothingness was a paradox. But as science advanced, particularly in the 20th century, our understanding of nothing changed dramatically. In modern physics, nothing is more than just an empty void. It's a seething, bubbling quantum field, a vacuum state that isn't truly empty. Even in what we consider nothing, particles and antiparticles are constantly appearing and annihilating each other. This quantum foam suggests that nothing might not be as empty as we once thought. So if nothing isn't really nothing, what does that mean for the beginning of our universe? Did the universe emerge from this quantum nothingness? And if so, what caused it? Throughout history, some of the greatest minds have wrestled with the concept of nothingness. What is it? Does it exist? And if so, how can we even comprehend something that is, by definition, the absence of everything? Let's start our journey with Plato, the ancient Greek philosopher who lived around 2,400 years ago. Plato believed in a dualistic reality, the world of forms, which is perfect and eternal, and the material world, which is imperfect and constantly changing. For Plato, the material world we perceive is only a shadow of the true reality, the world of forms. But what about nothingness? Plato didn't think of nothingness as a true state. Instead, he believed that everything, even a void, must have some form or essence. To him, absolute nothingness didn't exist because there was always some underlying form or potential. In other words, for Plato, nothingness was not truly empty. It was simply a lack of material manifestation of the perfect forms that existed in a higher reality. Moving on to Plato's student Aristotle. Unlike his teacher, Aristotle was more concerned with the material world. He introduced the idea of potentiality and actuality. For Aristotle, everything in existence had the potential to become something else. A seed, for instance, has the potential to become a tree. But what about nothingness? Aristotle argued that there was no such thing as pure nothingness. Even in a vacuum, there was potential, something that could be, but simply wasn't yet. To Aristotle, nothingness was just unrealized potential, waiting for the right conditions to bring something into existence. During the medieval period, the concept of nothingness took on a theological dimension. Philosophers like Thomas Aquinas and Augustine grappled with the idea of creation ex nihilo, creation out of nothing. Christian theologians argued that God created the universe out of nothing. This was a radical idea at the time, suggesting that before God's act of creation, there was absolute nothingness, no space, no time, no matter. But this nothingness wasn't the same as the philosophical nothingness of the Greeks. It was a profound absence, a void that could only be filled by divine intervention. This idea of nothingness as the starting point for all of creation profoundly influenced Western thought, intertwining with both philosophy and religion. As we move into the Renaissance, the French philosopher René Descartes brought a new perspective. Descartes is famous for his statement, cogito ergo sum. I think, therefore I am. For Descartes, doubt was a crucial tool. He doubted everything that could possibly be doubted, stripping away all assumptions until he reached the one thing that could not be doubted, his own existence. But what does this have to do with nothingness? Descartes' method implies that nothingness could be a state of pure doubt, a theoretical construct where everything is questioned and only the thinking self remains. In a sense, Descartes introduced a new kind of nothingness, a mental void, where the only certainty is the self. Finally, we arrive at Friedrich Nietzsche, the 19th century German philosopher known for his existential and often unsettling ideas. Nietzsche famously said, "If you gaze long enough into an abyss, the abyss will gaze back into you." For Nietzsche, the abyss represented a kind of existential nothingness, a void that humans might encounter when they confront the meaninglessness of existence. Unlike his predecessors, Nietzsche didn't shy away from the terrifying implications of nothingness. He suggested that confronting this void was a necessary part of human growth and self-overcoming. Nietzsche's abyss isn't just a physical void, it's a psychological and existential challenge. It's the nothingness we face when we question the very foundations of our beliefs and values. For Nietzsche, staring into this abyss is an opportunity, a chance to affirm life and create meaning where there appears to be none. From Plato's eternal forms to Nietzsche's abyss, the concept of nothingness has evolved dramatically through the ages. Philosophers have sought to understand it, define it, and even embrace it. But as deep and varied as these philosophical perspectives are, they are only one side of the story. In the next part of our journey, we'll explore how modern science has approached the idea of nothingness. What does physics tell us about the void? And could it be that nothingness is not as empty as it seems? Stay with us as we continue to unravel the mysteries of the universe. Imagine, if you can, the entire universe compressed into a single point, a point so small, so dense, and so hot that all the matter and energy we see around us today were contained within it. This is the beginning of our story, the moment before the Big Bang. But how did we get from this singularity to the vast expanding universe we see today? And what evidence do we have to support this incredible theory? The Big Bang Theory is the prevailing cosmological model that explains the early development of the universe. According to this theory, about 13.8 billion years ago, the universe began as an extremely hot and dense singularity. In an instant, less than a trillionth of a second, it began to expand, and it's been expanding ever since. As the universe expanded, it cooled, allowing particles to form and eventually coalesce into the stars, galaxies, and planets we see today. But how do we know this happened? What evidence supports the idea that our universe began in such a dramatic and violent way? One of the most compelling pieces of evidence for the Big Bang Theory was discovered by accident in 1965 by two radio astronomers, Arno Penzias and Robert Wilson. They were using a large horn-shaped antenna to study radio waves from space, but what they found was something completely unexpected. No matter where they pointed their antenna, they detected a faint, uniform signal, a kind of background noise that seemed to come from every part of the sky. At first, they thought it might be interference from nearby cities or even bird droppings on the antenna itself. But it soon became clear that this noise was something far more significant. What Penzias and Wilson had discovered was the cosmic microwave background radiation, or CMB, an afterglow from the Big Bang itself. This radiation is a snapshot of the universe when it was just 380,000 years old, a time when the universe had cooled enough for light to travel freely for the first time. So what exactly is the cosmic microwave background? The CMB is a form of electromagnetic radiation that fills the entire universe. It's the oldest light we can observe, dating back to the time when the universe first became transparent. Before this moment, the universe was a hot, dense plasma, an opaque fog of particles that trapped light. As the universe expanded, it cooled, and when it reached about 3,000 degrees Kelvin, protons and electrons combined to form neutral hydrogen atoms. This allowed light to finally travel freely through space, creating the CMB we observe today. The CMB isn't perfectly uniform. It has tiny fluctuations, differences in temperature as small as 1 part in 100,000. These fluctuations are crucial because they represent the seeds of all the structure in the universe today. Over billions of years, these small variations in density grew into the galaxies, stars, and planets that populate our universe. The discovery of the cosmic microwave background was a watershed moment in cosmology. It provided direct evidence that the universe had a hot, dense origin, as predicted by the Big Bang Theory. Subsequent missions like the COBE, WMAP, and Planck satellites have mapped the CMB in incredible detail, confirming the Big Bang model with stunning precision. These detailed observations of the CMB have allowed scientists to measure key properties of the universe, such as its age, composition, and rate of expansion. The match between the observed data and the predictions of the Big Bang theory is one of the strongest validations of this model. The cosmic microwave background isn't the only evidence supporting the Big Bang theory. In the 1920s, Edwin Hubble made a groundbreaking discovery when he observed that galaxies are moving away from us, and the farther away they are, the faster they're moving. This redshift of light from distant galaxies provides strong evidence that the universe is expanding. Hubble's discovery of the expanding universe was the first clue that the universe had a beginning, a moment when all matter and energy were compressed into a single point before expanding outward. This observation fits perfectly with the predictions of the Big Bang theory. Combined with the cosmic microwave background and the abundance of light elements like hydrogen and helium, which were formed in the first few minutes after the Big Bang, we have a coherent and compelling picture of our universe's origins. While the Big Bang theory is well supported by evidence, our understanding of the universe is far from complete. Questions remain about what caused the Big Bang, what happened in the first fraction of a second, and what lies beyond the observable universe. Future missions and observations, from studying dark matter and dark energy to exploring the possibilities of a multiverse, may hold the answers. The discovery of the cosmic microwave background was a monumental step in our quest to understand the universe, but it's just one chapter in an ongoing story. As we continue to explore the cosmos, who knows what new mysteries we'll uncover? One thing is certain, the echoes of the Big Bang will continue to guide us as we seek to understand our place in the universe. Imagine a time before time, a place before space, an existence where the laws of physics as we know them didn't apply. This is the realm of quantum fluctuations, the birthplace of the universe itself. But what are quantum fluctuations, and how could they have given rise to everything we see around us today? At the heart of quantum mechanics lies a strange and fascinating concept: quantum fluctuations. These are temporary changes in the amount of energy in a point in space, occurring spontaneously and unpredictably. In the quantum world, particles can appear out of nothing, exist for a brief moment, and then vanish back into the void. But how does this relate to the birth of the universe? To understand this, we need to step back and explore the nature of the quantum vacuum, a state that is often misunderstood as nothingness. In reality, the quantum vacuum is far from empty. It's a seething sea of energy, filled with these spontaneous fluctuations. And while they might seem insignificant, these tiny fluctuations could hold the key to the origin of the universe. During the earliest moments of the universe, just fractions of a second after the Big Bang, the entire cosmos was incredibly small, dense, and hot. In this extreme environment, quantum fluctuations played a crucial role. These fluctuations, which are normally confined to tiny scales, were stretched across the entire universe as it rapidly expanded in an event known as cosmic inflation. Cosmic inflation is a theory that suggests the universe expanded exponentially fast in the first moments of its existence, driven by a powerful force that we still don't fully understand. As the universe expanded, the quantum fluctuations that existed at that tiny scale were stretched to cosmic proportions, seeding the formation of galaxies, stars, and planets. But how do these tiny random fluctuations lead to the vast structures we see in the universe today? The answer lies in the nature of these fluctuations themselves. When the universe was incredibly small, quantum fluctuations created slight variations in the density of matter and energy. As the universe expanded, these tiny differences were amplified, with denser regions pulling in more matter and forming the galaxies and clusters we see today. In essence, the galaxies, stars, and planets we see today owe their existence to these early quantum fluctuations. Without them, the universe might have remained a smooth, featureless expanse of energy. Instead, these fluctuations provided the seeds from which all cosmic structures grew. Quantum fluctuations don't just offer an explanation for the structure of our universe. They also open the door to an even more mind-bending idea: the multiverse. According to some theories, our universe might be just one of many. each born from its own quantum fluctuation in a vast, possibly infinite, multiverse. In this view, quantum fluctuations could create not just one universe, but an endless number of universes, each with its own unique properties. Some might be similar to ours, while others could be vastly different. Alien realms with laws of physics that we can barely imagine. This idea, while still speculative, has profound implications for our understanding of existence. It suggests that our universe might not be the only one, and that quantum fluctuations could be the mechanism by which new universes are constantly being born. But what does the future hold for our universe? Will quantum fluctuations continue to shape its destiny? Some theories suggest that quantum fluctuations could play a role in the ultimate fate of the universe, whether it ends in a big freeze, a big crunch, or a big rip. In the big freeze scenario, the universe continues to expand, and as it does, quantum fluctuations might create new structures even as existing stars and galaxies fade away. In the big crunch, the universe could collapse back into a hot, dense state, possibly leading to another Big Bang, a cyclical universe born again from quantum fluctuations. And in the Big Rip, quantum effects could play a role in tearing apart the very fabric of spacetime itself. While we don't yet know which of these scenarios will play out, one thing is clear. Quantum fluctuations, those tiny, seemingly insignificant events, are fundamental to the very nature of our universe, from its birth to its potential death. Quantum fluctuations challenge our understanding of reality, blurring the lines between something and nothing. They suggest that the universe itself might have emerged from a quantum fluctuation, an event so small and fleeting, yet so powerful that it gave birth to everything we know. As we continue to explore the mysteries of the universe, we find that the tiniest events at the quantum level can have the most profound effects on the grandest scales. Perhaps in the end, it's these quantum fluctuations that remind us of the infinite possibilities contained within the fabric of reality itself. Imagine for a moment that our universe, vast and filled with billions of galaxies, might be just one of many. What if everything we know is just a small part of a much larger, unimaginable reality? This is the concept of the multiverse, a collection of multiple, perhaps infinite universes existing side by side. But what are these multiverse theories? And could our universe really be just one among countless others? The idea of the multiverse challenges our understanding of reality. Instead of one universe, some theories suggest there could be an entire ensemble of universes, each with its own laws of physics, constants, and even dimensions. These universes could be radically different from our own, or they might be nearly identical, with only slight variations. Multiverse theories arise from various branches of physics and cosmology, each proposing a different way in which multiple universes could exist. Let's explore some of the most intriguing and mind-bending ideas that scientists have put forward. One of the earliest and most famous multiverse theories comes from quantum mechanics, the many worlds interpretation. Quantum mechanics describes the strange and often counterintuitive behavior of particles at the smallest scales. One of its mysteries is that particles seem to exist in multiple states at once, only settling into a definite state when observed. The many worlds interpretation suggests that every possible outcome of a quantum event actually happens, but in separate, parallel universes. For example, when you flip a coin, in one universe it lands heads, and in another, it lands tails. Every decision, every random event creates a branching point, leading to a new universe. According to this theory, an infinite number of parallel universes exist, each one the result of different possibilities playing out. Another compelling multiverse theory comes from cosmology, specifically the concept of cosmic inflation. In the earliest moments after the Big Bang, the universe underwent a period of rapid expansion, known as inflation. But what if inflation didn't happen just once? What if it's an ongoing process, happening in different regions of space at different times? According to the inflationary multiverse theory, our universe is just one bubble in a vast, frothy sea of bubbles. Each bubble represents a different universe with its own unique properties. Some bubbles might collide, creating new universes, while others remain isolated, expanding forever. This theory suggests that the multiverse is not just a possibility. It's a natural consequence of inflation happening over and over again, potentially creating an infinite number of universes. String theory, a theoretical framework that seeks to unify all the fundamental forces of nature, offers another path to the multiverse. According to string theory, the basic building blocks of reality are not particles, but tiny vibrating strings of energy. These strings can vibrate at different frequencies, giving rise to the particles and forces we observe. But string theory also predicts the existence of extra dimensions beyond the familiar three dimensions of space and one of time. These extra dimensions could be compactified, curled up so small that we don't perceive them directly. However, in some versions of string theory, these extra dimensions allow for the existence of multiple universes, each with different physical properties, depending on how the dimensions are configured. In this view, our universe is just one possible configuration among countless others, each arising from the different ways these strings can vibrate and interact. The multiverse, in this sense, is a natural consequence of the complex and varied landscape of string theory. The concept of the multiverse raises profound questions about the nature of reality and our place within it. If multiple universes exist, each with its own version of events, what does that mean for our understanding of fate, free will, and even the nature of consciousness? In a multiverse, the idea of the one true reality becomes meaningless. Instead, reality could be a vast, branching network of possibilities, with every conceivable outcome playing out in some universe somewhere. This idea challenges our perception of identity and continuity, suggesting that there could be countless versions of you living out different lives in parallel universes. While these ideas might seem like science fiction, they are grounded in serious scientific theories and mathematical models. The multiverse is not just a speculative fantasy, it's a legitimate area of inquiry that could one day reshape our understanding of the cosmos. Despite the intriguing possibilities, the multiverse remains a hypothesis, one that is difficult, if not impossible, to test directly. However, scientists are searching for indirect evidence that could support the existence of a multiverse. For example, some researchers are looking for signs of collisions between our universe and other universes in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Others are exploring the mathematical implications of string theory and quantum mechanics, searching for insights that could reveal the nature of the multiverse. While direct evidence may be elusive, the pursuit of these ideas pushes the boundaries of our knowledge and challenges us to think beyond the confines of our own universe. The multiverse theory is one of the most fascinating and provocative ideas in modern science. It invites us to consider the possibility that our universe is just one of many, a single thread in the rich tapestry of existence. As we continue to explore the mysteries of the cosmos, who knows what we might discover? Perhaps one day we'll find that the multiverse is more than just a theory. It's the true nature of reality itself. Time is one of the most fundamental aspects of our existence. It governs our lives, dictates the flow of events, and shapes our understanding of the universe. But what if time itself had a beginning? And what does it even mean to ask if there was something before time began? To explore the idea of time before time, we first need to understand what time is. In our everyday experience, time seems to flow like a river, carrying us from the past, through the present, and into the future. But according to modern physics, time is much more than just a flowing stream. Albert Einstein's theory of relativity revolutionized our understanding of time by showing that time and space are interconnected. Together, they form a single entity known as spacetime. In this framework, time is not absolute. It can stretch, compress, and even bend depending on the presence of mass and energy. Time in this sense is a dimension, a coordinate that helps us locate events in the universe, just like the coordinates of space. But what happens when we go back in time, tracing the history of the universe all the way to its beginning? Can we go back before the Big Bang? To a time before time itself? The Big Bang theory suggests that the universe began about 13.8 billion years ago, starting from an incredibly hot and dense point known as a singularity. This event marked the beginning of both space and time. Before the Big Bang, There was no space, no matter, no energy, and crucially, no time as we understand it. In this view, time itself began with the Big Bang. Asking what happened before the Big Bang might be meaningless because before implies the existence of time. If time began at the Big Bang, there was no before, at least not in the sense we typically understand. Despite this, scientists and philosophers have proposed several theories about what might have existed before the Big Bang, or whether the concept of before even makes sense. One such theory is the idea of a cyclic universe, a universe that goes through infinite cycles of expansion and contraction, with each Big Bang marking the beginning of a new cycle. In a cyclic model, the universe doesn't have a true beginning or end. Instead, time as we know it could be part of an endless loop, with no first moment, just an infinite series of rebirths. Another idea is that our universe could be one of many in a multiverse, each with its own timeline. In this scenario, what we perceive as the beginning of time in our universe might be just one point in a much larger, timeless reality. Some scientists suggest that the Big Bang could have been caused by the collision of these bubble universes or by quantum fluctuations in a timeless state. In these models, time as we understand it might only apply within our universe, with the larger multiverse existing outside of time altogether. Quantum mechanics, which governs the behavior of the smallest particles in the universe, also offers intriguing insights into the nature of time. At the quantum level, particles don't follow the usual rules of cause and effect. They can exist in superpositions, where they are in multiple states at once, and can even tunnel through barriers in ways that seem to defy our understanding of time. These strange behaviors suggest that at the quantum level, time might not be as straightforward as we experience it. Some quantum theories propose that time itself could be an emergent property, a byproduct of more fundamental processes that we don't yet fully understand. If this is the case, time might not be a fundamental aspect of reality at all, but something that emerges only in certain conditions, like in our universe after the Big Bang. Philosophers have long pondered the nature of time and whether it makes sense to talk about a time before time. In ancient Greece, Aristotle argued that time is a measure of change, and without change, time has no meaning. According to this view, if there was no universe, no matter, no space, then there could be no time. In more modern times, philosophers like Immanuel Kant suggested that time might be a construct of the human mind, a framework we use to make sense of our experiences. If time is a mental construct, then the idea of a before the universe becomes a paradox, a question that cannot be answered because it assumes a framework that might not exist beyond our perception. The question of whether there was a before time is one of the most profound and challenging in both science and philosophy. It pushes the limits of our understanding and forces us to confront the very nature of reality itself. While we may never fully answer this question, the exploration of time's origins opens up new ways of thinking about the universe and our place within it. Whether time had a beginning or has always existed in some form, it remains one of the greatest mysteries of the cosmos. As we continue to explore the universe, perhaps we'll uncover more clues about the nature of time, the origin of everything, and what, if anything, lies beyond the boundaries of our understanding. For as long as humanity has existed, we have looked to the skies, the earth, and the stars, searching for answers to the most profound question: where did we come from? Across cultures and religions, people have developed a rich tapestry of stories and beliefs about the creation of the world and the universe. These creation myths not only tell us about the origins of existence, but also about the values, hopes, and fears of the societies that created them. Creation myths are among the most ancient and enduring stories known to humanity. They are the narratives that explain how the world came into being, often involving gods, supernatural forces, and primordial elements. These myths serve as a foundation for understanding not only the physical universe, but also humanity's place within it. Let's explore some of the most influential creation stories from different religious and cultural traditions. One of the most well-known creation stories comes from the Judeo-Christian tradition, as described in the book of Genesis. In the beginning, God created the heavens and the earth. These opening words of the Bible set the stage for a 7-day creation process, where God brings order to chaos, separates light from darkness, and creates the sky, land, seas, plants, animals, and finally, humanity. In this narrative, the universe is the deliberate and purposeful creation of an all-powerful God. Each element of the world is created with intention, culminating in the creation of human beings who are made in God's image and given dominion over the earth. This story has profoundly influenced Western culture, shaping views on humanity's relationship with the natural world and the divine. In Hinduism, creation is seen as an eternal cycle of birth, death, and rebirth. The universe is created, destroyed, and recreated in an endless loop. One of the central stories of creation involves the god Vishnu, who rests on the cosmic serpent Ananta in the primordial ocean. From Vishnu's navel emerges a lotus flower, and from this lotus, Brahma, the creator god, is born. Brahma then creates the universe, including the heavens, the earth, and all living beings. However, this creation is not permanent. After a cycle of many eons, the universe dissolves back into the primordial waters, only to be created again. This cyclical view of time and creation reflects the Hindu belief in the eternal nature of the cosmos and the interconnectedness of all life. In ancient Egyptian mythology, creation begins with the god Ra, who emerges from the chaotic waters of Nun, the primordial ocean. Ra, often depicted as the sun, brings light and life to the world. According to one version of the myth, Ra creates the world by speaking it into existence, naming each element and thus bringing it forth from the chaos. The Egyptian creation myths emphasize the power of the spoken word and the importance of order emerging from chaos. The daily rising and setting of the sun were seen as a continual act of creation, with Ra battling the forces of chaos each night to ensure the world's renewal each morning. These myths reinforce the Egyptians' belief in the stability and order of the cosmos, which was reflected in their society's emphasis on Mat, the concept of truth, balance, and harmony. The Navajo people of the American Southwest have a rich creation story that describes the emergence of the world from a series of underworlds. According to Navajo tradition, the first world was a small, dark place inhabited by insect-like beings. These beings journeyed through successive worlds, each larger and more complex than the last, until they reached the present world, known as the Fourth World. In this Fourth World, the Holy People, or Diendinae, taught the Navajo how to live in harmony with nature and the cosmos. The creation story emphasizes the importance of balance, respect for the earth, and the interconnectedness of all living things. It reflects the Navajos' deep spiritual connection to the land and their belief in the sacredness of the natural world. Creation myths are more than just stories. They are expressions of humanity's deepest beliefs and values. Each culture's creation story reflects its unique worldview, offering insight into how people understand their place in the universe. Whether through the word of a single creator, the emergence from chaos, or a journey through different worlds, these myths provide a framework for understanding the origins of life, the nature of the cosmos, and the relationship between the human and the divine. While the specifics of these stories vary, they all share a common theme: the desire to make sense of the world and our existence within it. In exploring these diverse perspectives on creation, we gain a greater appreciation for the rich tapestry of human thought and the enduring quest to understand the mysteries of the cosmos. Our universe is vast, complex, and awe-inspiring. We've made incredible strides in understanding the cosmos, from the tiniest subatomic particles to the largest galactic clusters. Yet despite all we've learned, there are still profound mysteries that elude us. These are the questions that keep scientists, philosophers, and thinkers up at night. The things we still don't know. One of the biggest mysteries in modern cosmology is dark matter. We know it exists because of its gravitational effects on galaxies and clusters of galaxies. Without dark matter, the stars in galaxies would fly apart due to their high rotational speeds. But what exactly is dark matter? Despite its name, dark matter isn't just dark, it's invisible. It doesn't emit, absorb, or reflect light, making it impossible to observe directly. Scientists estimate that dark matter makes up about 27% of the universe's mass and energy, yet its true nature remains one of the most elusive puzzles in astrophysics. Is it made of undiscovered particles, or is it something entirely different? We don't yet know. If dark matter wasn't mysterious enough, there's also dark energy, a force that's even more perplexing. In the late 1990s, astronomers discovered that the universe's expansion is accelerating, not slowing down as previously thought. This acceleration is driven by something we've named dark energy. But what is it? Dark energy is believed to make up about 68% of the universe, yet we know almost nothing about it. Is it a property of space itself, a new kind of energy field, or something even more exotic that we haven't yet imagined? The true nature of dark energy is one of the greatest mysteries in cosmology, and solving it could fundamentally change our understanding of the universe. Closer to home, we face another profound question. How did life begin? The origin of life on Earth is a mystery that spans multiple scientific disciplines, from biology to chemistry to geology. We know that life began billions of years ago in Earth's oceans, but how did non-living chemicals give rise to the first living organisms? Several theories have been proposed, including the idea that life began in deep-sea hydrothermal vents, or that it was sparked by lightning in the early atmosphere. Another possibility is that life, or at least the building blocks of life, came to Earth from space on meteorites, a theory known as panspermia. Despite these theories, we still don't have a definitive answer to how life began. It's a puzzle that continues to challenge and inspire scientists around the world. Even more mysterious than the origin of life is the nature of consciousness. How does a collection of atoms and molecules give rise to the rich, subjective experience we call consciousness? How do thoughts, emotions, and self-awareness emerge from the physical processes in our brains? Consciousness is a mystery that has puzzled philosophers and scientists for centuries. Some theories suggest that consciousness arises from the complexity of neural networks, while others propose that it could be a fundamental aspect of the universe, much like space and time. We don't yet have a clear answer, and the study of consciousness remains one of the most intriguing and challenging fields of research. While we grapple with the mysteries of the present, we also wonder about the future. What is the ultimate fate of the universe? Will it continue to expand forever, gradually growing colder and darker until all stars burn out and galaxies drift apart in what's known as the Big Freeze? Or will gravity eventually pull everything back together in a big crunch, leading to a new Big Bang? Some theories even suggest the universe could tear itself apart in a big rip, where dark energy's influence grows so strong that it overcomes all other forces, ripping galaxies, stars, and even atoms apart. Each of these scenarios presents a different vision of the universe's end. But which one, if any, will come to pass? We don't yet know. The mysteries we've explored today remind us of how much we still don't know about the universe, life, and our own existence. These unanswered questions are not just scientific puzzles. They are profound challenges that touch on the very nature of reality and our place within it. As we continue to explore and learn, each discovery opens new doors, revealing even more questions and mysteries waiting to be solved. Our journey of discovery is far from over. In fact, it's just beginning. The more we learn, the more we realize how much there is still to uncover. And that's the beauty of science and human curiosity. Each mystery is an invitation to explore, to question, and to wonder. So as we look up at the stars and ponder the unknown, we should embrace the mysteries we haven't yet solved, for they are the driving force behind our quest to understand the universe. We've journeyed through the vast and mysterious concept of nothing, a word that seems so simple, yet holds profound implications for our understanding of the universe. From the earliest philosophical musings to the latest scientific theories, the idea of nothing has challenged us to rethink what we know about existence, reality, and the cosmos itself. We began by exploring the nature of nothing in both philosophy and science. Ancient philosophers grappled with the paradox of nothingness, while modern physicists revealed that even in what we perceive as empty space, there's a seething sea of quantum activity, a state that defies our traditional understanding of nothing. We then delved into the origins of the universe, considering the Big Bang as the moment when time, space, and everything we know burst forth from what might have been nothing, or something incredibly different from our current reality. We explored quantum fluctuations, tiny blips in energy that could have given rise to the entire cosmos, suggesting that nothing may never have truly existed. Finally, we examine various theories and perspectives, from the multiverse to cyclic models of the universe, each offering different ways to think about what, if anything, existed before the universe as we know it. Through these explorations, we've seen that the concept of nothing is not just an absence, it's a gateway to some of the most profound questions we can ask. As we reflect on our journey, it becomes clear that nothing is far more complex than it appears. It challenges us to confront the limits of our knowledge and to consider possibilities that stretch the boundaries of imagination. The concept of nothing forces us to ask, can there ever truly be nothing? Or is what we call nothing simply the absence of something we've yet to comprehend? This journey through nothing reminds us that the universe is full of mysteries that defy easy answers. The more we explore, the more we realize how much there is still to discover. And while we may not have all the answers, the pursuit of these questions is what drives science, philosophy, and our innate human curiosity. The mysteries of the universe, including the enigma of nothing, invite us to think deeply about our place in the cosmos. They encourage us to look beyond the surface of what we know and to embrace the unknown with wonder and curiosity. Each question we ask, each mystery we ponder, brings us one step closer to understanding the profound nature of reality. As we conclude this exploration, I encourage you to keep asking questions, to keep seeking out the mysteries that challenge our understanding. The universe is vast, and our journey through it is just beginning. The concept of nothing is a reminder that even the most seemingly simple ideas can hold the deepest secrets of existence.